Good morning, all of you. Welcome back to the hydraulic turbines topic. We have been in Unit 4 of hydraulics and hydraulic machinery subject. Now we are dealing with the hydraulic turbines. This is the second module in the hydraulic turbines. In the previous module, we have seen about what is hydraulic turbine and what are the various elements of hydroelectric power installation, and when do you classify depending on the head available for a hydroelectric power installation, various heads, definition of efficiencies like gross head, net head, and coming to the efficiencies, hydraulic efficiency, mechanical efficiency, volumetric efficiency, and the overall efficiency. Also, we have seen about the classification of turbines we discussed, like and turbines are classified based on the hydraulic action, like impulse type turbine, reaction type turbine, based on the direction of flow of water, tangential flow, axial flow, mixed flow, and radial flow turbines. And then depending on the head available, high head turbine, medium head turbine, low head turbine. And the fourth classification is depending on a characteristic number, type characteristic number, specific speed, low specific speed, medium specific speed, and high specific speed turbines. Okay, and we quoted certain examples also, like Pelton wheel, Francis turbine, John Wall turbine, Girard turbine, Thomson turbine, Porteran turbine, propeller turbine, Kaplan turbine. Several turbines we have mentioned as the examples for different varieties of these turbines under various classifications. As per our syllabus and content, we try to limit it to 3 or 4 turbines like Pelton wheel, and then modern Francis turbine, Kaplan turbine, and propeller turbine. These are the turbines that we discuss in this unit. We start with the Pelton wheel. Pelton wheel, sometimes called Pelton turbine, both mean the same. So this is a most commonly used impulse type turbine. Yesterday we defined what is impulse type turbine. At the exit of the nozzle, at the tip of the nozzle, all the available energy gets converted into only kinetic energy. Only kinetic energy. Such type of turbine is called impulse type turbine. If a part of the total hydraulic energy gets converted into kinetic energy and the rest, a substantial portion, remains in the form of pressure energy, we have other type of turbine, reaction turbine. The one which we are now dealing with is the Pelton wheel, which belongs to the class of impulse type turbine, where the total available energy is converted into kinetic energy only. So what about the pressure energy then? The pressure energy is 0 at the tip of the nozzle. That means it is the gauge pressure is 0, which indicates that the jet exerts into atmospheric pressure. So the Pelton wheel or the impulse type turbines work under atmospheric pressure. It works under a head, requires small quantity of water. The water requirement is small, that means discharge requirement is less, but the head over which it has to function is so high. We have seen it may be of the order of more than 250 meters. Of course, though the figures are indicative, like 250, 60, 10, and so on, are indicative figures, but it works under a very high head of the order of 250 meters or so. So, most commonly used impulse type turbine works under very high head, requires small quantity of water. The discharge requirement is small. Q is less, but H is more. We know the power developed is directly proportional to Q and H, discharge and head. So definitely it can develop huge amount of power because it is working under high head, even though the discharge is less. Water is taken to the turbine from the reservoir through penstocks, large diameter pipes, which are connected from the reservoir to the entrance of the turbine under are the penstocks, and the water is drawn through these penstocks. The penstock is a large pipe fitted with a nozzle at the end. This nozzle is fitted in order to have the conversion of the hydraulic energy fully into kinetic energy. Water comes out of the nozzle in the form of a jet. Because a nozzle is fitted, a jet of water is issued from the nozzle. The jet of water is issued from the nozzle, strikes the buckets in the direction tangential to the wheel. So this is how Pelton wheel is belonging to the class of a tangential flow turbine. What is tangential flow turbine? The liquid, the jet of liquid moves in a direction tangent to the path of rotation of the turbine runner. Path of rotation of the turbine runner. So it is called the tangential flow turbine. So the jet of water is issued from the nozzle. It strikes the buckets in the direction tangential to the wheel. The impact of water imparts a dynamic force to the wheel and the wheel starts moving. The water coming out of the wheel is discharged into the tail race. After it is striking, after the work is done, the liquid, the water gets collected into the tail race. We have a small video depicting the information relating to the working of Pelton wheel.
Pelton turbine.
Water energy is available at high head and low flow rate. Working of Pelton turbine is simple. High-speed water jet is ejected through a nozzle. When this jet hits buckets of Pelton wheel, it induces an impulsive force. This force makes the turbine rotate. In short, Pelton turbine transforms kinetic energy of water jet to rotational energy. The rotating shaft runs a generator and produces electricity. But demand of power may fluctuate over time. A governing mechanism, which controls position of spearhead, meets this requirement. With lowering power demand, spearheaded water inlet nozzle is moved in, so that water flow rate is reduced. If power demand increases, spearhead is moved out. This will increase flow rate. This in turn makes sure that turbine will rotate at a constant specified RPM, which conforms to the power supply frequency. So this mechanism acts as a speed governing mechanism of Pelton wheel. A cut is provided on bottom portion of buckets. This makes sure that water jet will not get interfered by other incoming buckets. One of the most important parameter of Pelton turbine design is number of buckets on the disc. If number of buckets is inadequate, this will result in loss in water jet. With lowering number of buckets, at some point of operation, complete water jet might be lost. This will decrease efficiency of Pelton turbine drastically. So there should be an appropriate number of buckets, which will make sure that no water is lost. Most vital component of Pelton wheel is its bucket. Buckets are casted as single solid piece in order to avoid fatigue failure. Water jet is split into two equal components with help of a splitter. The special shape of bucket makes the jet turn almost 180 degrees. This produces an impulsive force on bucket. Force so produced can easily be derived from Newton's second law of motion. Blade outlet angle close to 180 degrees is usually used in order to maximize impulsive force. Absolute velocity of fluid will have huge drop from inlet to exit of bucket. However, pressure remains same. So Pelton turbine gains mechanical energy purely due to change in kinetic energy of jet, not due to enthalpy change. Which means Pelton turbine is a pure impulse machine. Pelton turbine design is always aimed at extracting maximum power from water jet, or maximizing efficiency. Power extraction is maximum when product of impulsive force and bucket velocity is maximum. If Pelton wheel buckets are held stationary, Even if there is huge impulsive force, power extraction will be zero. Similarly, if buckets are moving with same speed of jet, water jet won't be able to hit the bucket, which leads to zero impulse force. Again, power extraction will be zero. In short, power extraction is zero, both at zero bucket speed, and when bucket speed is same as jet speed. So, optimum power extraction happens in between. It can be shown using Euler's turbomachinery equation that maximum power extraction happens when bucket speed is half the jet velocity. So it is always desirable to operate Pelton wheel at this condition. Pelton turbines can give efficiency as high as 90% at optimum working conditions. Hope you got a good understanding on working of Pelton turbines.
Okay, so this is the working of a Pelton turbine. A small AV is shown about various components of the Pelton turbine. The central portion is the wheel here. Over the periphery of a wheel, number of buckets are connected, mounted, and these are all the buckets or vanes. And the shape of the bucket also is double hemispherical shape. More number of buckets are connected over the periphery of a wheel with the intention that when the liquid jet is coming out from the nozzle, no amount of this liquid jet should be wasted without striking the buckets. Thereby, you will be able to develop more power. That is the reason why we have optimum number of buckets. Let us see how many number of buckets are to be provided, etc. But we try to provide maximum number of buckets over the periphery of wheel in order to see that the liquid jet which is emerging from the nozzle should strike completely without wasting the quantity of water. Jet water should not be wasted. It should be continuously striking either one jet or the other jet. So with that intention, maximum number of buckets are connected over the periphery of a wheel. The shape of the bucket also you can see here like double hemispherical shape. That means like two half cups joined together with a central portion as a splitter where the liquid jet directly strikes at the splitter. Also, it is shown in the video that the velocity of the bucket should be half of the velocity of the jet to achieve the highest efficiency. That also we will see the derivation how it would be. The like small u, the velocity of the bucket should be equal to half of the velocity of the jet to achieve the maximum efficiency. As we understood, the various components of the Pelton wheel are nozzle with control mechanism, buckets and the runner, of course a casing to cover the entire portion of the Pelton wheel, hydraulic brake and deflector. Let us see one by one how these components are arranged in a hydroelectric power station, in a hydraulic turbine, and what is the main purpose of these components. First one is a nozzle with control mechanism. A nozzle is fitted at the end of the penstock to convert the hydraulic energy into kinetic energy. In the figure you can see, if this is the penstock carrying water from the reservoir, at the end of the penstock, this nozzle is provided. Nozzle is a part of a pipe. The cross-sectional area is reduced. At the tip of the nozzle, you have the maximum kinetic energy for this jet of water. So this is the nozzle with a control mechanism. So what is the control mechanism here? You have a spear which is provided. This is called the spear rod, and this spear rod is provided with a spear at its end. This is directly connected to the governor of a hydraulic turbine. The purpose of this spear, of course, first of all, the spear rod will have a simple harmonic motion. It will have a simple harmonic motion. You can see here towards the exit of the nozzle, the cross-sectional area is decreasing. Suppose if this spear is pushed inwards, towards this, more area of flow would be blocked. The cross-sectional area of flow would be blocked by this spear. If the cross-sectional area is blocked there, what will happen? The discharge Q is equal to area into velocity. If the area is reduced because of this blockage of the spear, naturally the discharge will be reduced. So, to have a lesser discharges, to control the flow of water through this penstock through this nozzle, we have this spear regulation arrangement. Why should we control? We need to control this because we need more power sometimes, we may need less power sometimes. The power generation and power utilization would be going together, as a result of which if there is no power demand, probably we may need to reduce the discharge, or sometimes we may have to shut off totally the hydroelectric power station not to operate. Okay, so this is how there is a spear rod connected, and this spear rod with the help of the governing mechanism will have simple harmonic motion, to and fro motion. If less discharge is required, which may be resulting in less power generation, the spear rod will be pushed inwards, thereby the flow section available, the cross section area of the flow section available would be reduced. Discharge would be reduced. Power generated is directly proportional to discharge into head. Since the discharge is reduced, the power generated also would be, power developed also would be reduced. On the other hand, you need more power to be developed. That means more discharge is required. So to have the more discharge here, this spear rod will have a backward motion. Instead of having a forward motion, it will have a backward motion. So through this governing mechanism, once again, it's all fully automated. So if this rod is moving outwards, naturally the spear also moves outwards, allowing more passage for the flow at this nozzle. If more passage is there, more cross-sectional area, and hence more discharge area into velocity. Since there is more discharge, the power developed also would be equal to gamma QH. Q is more, the power developed also will be more. So to meet the more power demand. So this is what a nozzle with a control mechanism. Next, buckets and runner. This is another important component in a Pelton wheel. You already seen this in the figure, that you have the runner, what we call is a runner or a rotor, which is having number of buckets connected over its periphery. Pelton wheel is fitted with the buckets having the shape of double hemispherical cup. You can see in the figure, this is one cup. The one cup is shown here separately. It is something like one half cup here, another half cup here. They are joined together at a sharp vertical edge. This portion is a sharp vertical edge, and this is called splitter. The liquid jet strikes at this splitter only. So each bucket is divided into two parts by a sharp vertical edge at the center, which is known as a splitter. Something like this is one cup, this is another cup. They join together. The central portion is the splitter. The liquid jet strikes at this splitter. You can see here the cross section of this. You can see the cross section of this bucket. So the black portion shown in the figure is the bucket, and the liquid jet is striking at the splitter, and it is getting reflected after gliding over the surface of the bucket on both the sides, and leaves at this outlet tip. The jet impinges on the splitter and is divided into two parts. Each part of the jet glides over the bucket and comes out at the outer edge of the bucket. So inlet tip is the splitter and outlet tip is this portion. This outer edge is the outlet tip. So the rear of the buckets is so shaped that the water coming out of the buckets does not interfere with the jet striking the following bucket. So what will happen, because you have number of buckets connected here, when the liquid jet is striking one bucket, the liquid jet moves away and immediately the next bucket comes in position. So in this process, when the liquid jet is coming out, when it is moving and next bucket is coming, it should not strike in the backward direction. Otherwise, there will be back thrust. So the angle is so shaped that it will not interfere with the jet striking the following bucket. So we can see here once again the same cross section of the vein or the bucket shown here. So this is the bucket. This is the shape of the bucket, like two half cups joined together. The central portion is called the splitter, and the liquid jet directly strikes at the splitter. After striking at this portion, it glides over the surface of the bucket on both the sides and leaves at its outlet tip. So the angle at the outlet tip varies from 10 to 20 degrees, deflecting the jet to about 172 160 degrees. So angle of deflection of the jet would be around 160 to 170 degrees. The buckets are usually fastened to the wheel by means of bolts, so that the worn out buckets can be easily replaced. That is the advantage. Instead of completely making it as a monolithic unit, it is always better to fix with the help of the nuts and the bolts. Thereby, if any bucket is worn out, it can be replaced easily by removing it and keeping it a new one. Okay. Next component is the casing. Since the water flowing in the passage is at atmospheric pressure, the casing has no hydraulic action to perform. Contrary to this, in the case of a reaction turbine, you have the pressure energy also along with the kinetic energy. But in the case of Pelton wheel, it is only the atmospheric pressure. Either inside or outside, the pressure is only atmospheric pressure. So there is no specific hydraulic action that is there for the casing, but it prevents the splashing of water. When the liquid jet is striking here, the water will have a tendency to splash out. So this splashed water can be controlled by keeping a casing like this, which encloses the entire runner. So since the water flowing in the passage is at atmospheric pressure, the casing has no hydraulic action to perform, and it is provided to prevent the splashing of water. Next component is hydraulic brake. The runner goes on revolving for a considerable time due to inertia, even after the nozzle has been closed. When do you close the nozzle? Suppose if there is no water, or you don't want to run the turbine hereafter. Why you don't want to run the turbine? You don't require power. There is no power demand. There is no people to utilize it. Maybe after 10 o'clock in the night, probably all people may switch off their lights and they may go to bedroom, they try to sleep off, and the requirement may be limited. The power demand may be limited. If the power demand is limited, the power generation also should be limited. It should match. It should match directly. So what will be done there? Some of the units may be stopped. You have say 10 turbines, say in Sri Sailam or Nagarjuna Sagar, you have 10 turbines or 8 turbines. One turbine is not required, or 4 turbines are not required to be utilized because there is no demand. So there will be peak demand, off-peak demand for the power. So accordingly, the power generation should take place. So in this case, what will happen? You don't require the hydraulic turbine to run. One turbine is to be stopped. So what do? We try to stop this turbine by stopping the flow of water. So there will be no movement of water here. There may be certain walls. With the help of the gradual closure of the wall, this will be the water supply into the turbine runner through this jet will be stopped. Even after stopping also, the turbine runner rotates because of inertia. Because there is inertia, the turbine runner still rotates. So in order to bring to the standstill position at a faster pace, what we do? We provide another nozzle, which is called the hydraulic brake or brake nozzle, which flows in, which allows the turbine runner to rotate in the opposite direction. So this will have a tendency, because the liquid jet is striking here, the runner is moving in the anti-clockwise direction. But when the liquid jet is coming and striking the bucket and the back side of the bucket, it will have a tendency to move in the clockwise direction. Thereby the runner comes to the standstill position at a faster pace. Next is the deflector. When the load on the turbine decreases, the water supply has to be cut off by closing the valve. Just now we have seen, when you don't require to run the turbine, it should be stopped. So there is no load, there is no demand, there is no power demand. The sudden closure of the valve or the nozzle may cause excessive water hammer. This is a very, very important point. When the water is not required, when there is no power, so there is no power demand, then what we do? We try to stop the turbine runner. When you wish to stop the turbine runner, there will be a valve which may allow us to close. If you close the valve, what will happen in a penstock pipe? That you need to understand. If you stop or if you close the valve when the water is flowing in the penstock pipe, simply apply the pipe principles. Bernoulli's equation you may apply. When the water is flowing in the pipe, it possesses both pressure energy as well as kinetic energy. Because it is moving, the liquid is moving in the pipe, so it possesses kinetic energy. It is enclosed in a cross-sectional area which is completely filled with the liquid, so it will have pressure energy. So hydraulic energy will be there in the form of both the kinetic energy as well as pressure energy. So such a type of flow of liquid you would like to stop by keeping a valve, by closing the valve. If you start closing with the help of a valve, already the water is flowing in the penstock pipe with certain hydraulic energy, kinetic energy as well as pressure energy. So when you are stopping, suddenly the movement of water, naturally the velocity is brought to zero. The velocity of flow of water is brought to zero. If the velocity is brought to zero, the kinetic energy is brought to zero. That means, since the total energy is constant by applying the Bernoulli's principle, this kinetic energy must have been converted into pressure energy. So the pressure energy will be abnormally increased, which may cause bursting of the pipe also, which may cause the bursting of the pipe. So the sudden closure of the nozzle may cause the excessive pressures leading to the water hammer. So to avoid this water hammer, the nozzle is closed slowly, and some of the water which is coming out of the nozzle will be deflected away from the bucket without striking the bucket. The water which is coming out of the nozzle will be deflected to go to tail race directly. So this arrangement is known as deflector. So in a movable steel plate, this will be provided, and this is what is called the deflector. The moment you don't require the power to be generated, the water supply should be cut off. If you start cutting off the water supply suddenly, the penstock pipe may burst. So to avoid the problem of this water hammer, what we do, we try to deflect the water. The nozzle will be closed slowly. In the meantime, whatever water that is flowing through the nozzle will not strike the bucket, and it will be directly moved or deflected to go to the tail race. So jet deflectors have the function of diverting the water or part of it between the nozzle and the runner in such a way that it does not hit the buckets. If it is not striking the bucket, the problem will be solved, the runner will not be rotating. Okay, they may be used in an emergency situation also. So in a nutshell, to say, we have discussed about several components of a Pelton wheel, and we have seen that it is an impulse type turbine. It works under atmospheric pressure, and there will be a number of cups or buckets which are provided over the periphery of a wheel, and the shape of these buckets is double hemispherical cup, also called double semi-ellipsoidal cups. Both mean the same. Double hemispherical, semi-ellipsoidal cups will be provided, and the buckets or cups are so shaped that the outlet angle will be about 10 to 20 degrees. Thereby, the jet deflects through an angle of 160 to 170 degrees to achieve the maximum hydraulic efficiency. So these buckets are made of cast steel, bronze, and stainless steel, and the deflected angle of the jet may be about 160 to 170 degrees. There will be spear regulation arrangement to control the quantity of water at the nozzle, and when the shaft of the wheel is horizontal, we should not provide more than 2 jets. This is all based on the practical conditions while the liquid jet is coming out and striking the buckets. So based on the practical condition, for a horizontal jet, for the horizontal shaft wheel, you have 2 nozzles, and maximum you have 6 nozzles and 6 jets will be there for a vertical shaft turbines. The casing will be there, and the purpose of the casing is there is no hydraulic action to perform, since the Pelton wheel is an atmospheric pressure turbine and it prevents the splashing of water. Let us look at the working proportions of this Pelton wheel. What is this velocity of jet? The theoretical velocity of the jet is given by simply root 2gh. V is equal to root 2gh, where h is the net head at which the turbine works. That means gross head minus the losses is the net head. And how do you get the gross head? The gross head will be the level difference between the head race to the tail race minus all the hydraulic losses will lead to the net head, and the theoretical velocity will be root 2gh. However, the actual velocity would be by considering the coefficient of velocity Cv. So the actual velocity of the jet is V is given to be Cv into root 2gh, and Cv is called the coefficient of velocity and the value of CV may be about 0.98 or 0.99. 0.98 or 0.99. This is about the velocity of the jet. Number 2, theoretical power. The power from water can be estimated from the expression like PT, theoretical power, would be equal to gamma QH. We have been mentioning that the power developed can be known to be directly proportional to the product of discharge and head, or P is equal to gamma QH. H is the head available, Q is the discharge is applied, and gamma is the unit weight of water. Gamma is the unit weight of water. So the theoretical power is also called the water horsepower, WHP, because it is a power which is obtained from water, so it is called water horsepower, WHP. The power supplied to the runner would be the theoretical power minus the power which is lost in the nozzle. So P1 would be equal to water horsepower if the losses in the nozzle are neglected, or it will be minus losses to get the actual power. So the actual power developed by the Pelton wheel is called the shaft horsepower, SHP, which would be equal to WHP multiplied by the overall efficiency, eta naught. Eta naught is the overall efficiency, and hence the power developed from any turbine would be equal to eta naught into gamma QH. Eta naught into gamma QH. H is the head of the turbine. For a Pelton wheel, it is about 152, 53, 50 meters and so on. Q is the discharge supplied, and gamma is the unit weight of water, 9810 Newton per meter cube, or 9.81 kilonewton per meter cube in standard conditions. And eta naught is the overall efficiency. So if these things are known, we'll be able to calculate how much power can be developed from a given turbine installation, so many kilowatts, so many megawatts, like that. Next is angles. So angle phi varies from 10 to 20 degrees. So what is this angle phi? Which will be directly reflecting the jet deflection. So the average value may be about 15 degrees, may be taken because the jet is deflected through an angle of about 160 to 170 degrees with respect to inlet to the outlet. Then diameter of the jet. How much diameter should be provided for the jet? So if the nozzle is provided, which is connected to the penstock, at the end of or at the tip of the nozzle, whatever is the diameter is there, through the diameter the liquid jet emerges out. So how to fix the diameter of this jet? The diameter of the jet may be obtained if the discharge is known, as simple as Q is equal to area into velocity. Q is equal to area into velocity. And if you know the velocity, actual velocity, then you will be able to calculate the area A would be equal to pi by 4 d square, which is equal to discharge Q divided by the actual velocity VA. The discharge Q divided by, how do you get the actual velocity? Just now we have seen theoretical velocity is root 2 GH, and CV, the coefficient of velocity multiplied by root 2 GH gives you the actual velocity. So the diameter from there can be computed to be equal to 4Q divided by pi CV root 2 GH whole to the power half. The large size of the jet is about 30 centimeters. Usually the diameter of the jet may be less, but we may have more number of jets also. We have seen like for a horizontal shaft turbine, maximum 2 jets can be provided. For a vertical shaft turbine, we may have 6 jets also. Next, speed ratio. The speed ratio is the ratio of the velocity of the wheel at pitch circle to the theoretical velocity of the jet. What do you mean by this pitch circle? So you have the runner. This is the runner, okay, and the buckets are connected over the periphery of a wheel. Diameter of the runner here may be referring to the actual diameter of the runner. But if you look at the outer diameter, after considering all the buckets connected, you have one more circle. Inner circle and outer circle is there for the runner. So the pitch circle is the circle which is drawn considering the centers of all these buckets. So you have inner circle, you have outer circle. In between, you have one more circle which is drawn by taking the centers of all the buckets, center points of all the buckets, and the line joining those points. If you draw, you will get a pitch circle. That circle is called the pitch circle. So the speed ratio is the ratio of the velocity of the wheel to the pitch circle, at the pitch circle to the theoretical velocity of the jet. Theoretical velocity is root 2 GH. Theoretical velocity is root 2 GH, and hence Ku, the speed ratio, would be equal to small u divided by ku root 2gh. Small u, if d is the diameter of that pitch circle, if d is the diameter of that pitch circle, then pi dn by 60 is the velocity small u, the tangential velocity small u divided by root 2gh. So the mean value of the speed ratio may be about 0.43 to 0.47. Of course, you may have the average value in the absence of any information. You may assume average value 0.45. Coefficient of velocity is different from speed ratio. Coefficient of velocity is something related to the jets, where accounting for the losses, the value of CV may be of the order of 0.97 to 0.99. Whereas here, the speed ratio, which is the ratio of u by root 2gh, u to the theoretical velocity root 2gh, may be of the order of 0.43 to 0.47. Next, mean diameter of the wheel. This pitch circle diameter is called the mean diameter, which may be calculated based on this. U is equal to the tangential velocity, also called the peripheral velocity, would be equal to pi dn by 60. Pi dn by 60. D is the diameter of the runner in a loose sense. Strictly speaking, it is the diameter of the pitch circle. How do you calculate that? U is equal to pi dn by 60. From there, you'll be able to calculate D. D is equal to 60 u by pi n. 60 u by pi n. So how do you get this u, the tangential velocity, or the velocity? The velocity at the pitch circle. How do you get that? This will be calculated based on root ku into root 2gh. So your ku is equal to u by root 2gh, or u is equal to ku into root 2gh. Once ku is assumed appropriately, you will be able to get the value of u. Once you get the value of u, you can substitute here. U 60 into u by pi n gives you the diameter, mean diameter of the wheel, mean diameter of the wheel. Then the jet ratio, another working proportion. The ratio of the pitch diameter to the jet diameter is called the jet ratio, capital D by small d. Small d is the diameter of the jet, and capital D is the pitch circle diameter or mean diameter of the runner. So you have capital D by small d is called the jet ratio. And for maximum efficiency, the value of jet ratio may be between 11 to 14. It could be this way, that way, little more may be there, but efficiency may not be maximum in that condition. So the jet ratio varies from 11 to 14 in order to achieve the maximum efficiency. The average value of this jet ratio m may be about 12. Then how do you fix the size of the buckets? We have seen these are all the buckets. No? These are all the buckets which are connected. So how to fix the size of these buckets? For each of these buckets, the radial length with respect to the center of this circle, the radial length of the bucket may be about 4 to 5 times small d. What is small d? Small d is the diameter of the jet. So if small d is known in terms of small d, you will be able to compute the radial length, axial width, and the depth of the bucket which is required to be provided as the splitter may be known in terms of this small d, 4 to 5d or 3 to 5d and 0.8 to 1.d, and where d is the diameter of the jet. How many such jets to be provided over a wheel? Number of jets. When the Pelton wheel is to develop more power, it is fitted with a number of jets. A Pelton wheel fitted with more than one jet is known as the multiple jet Pelton wheel. We have seen maximum 2 number of jets can be there. Maximum 2 number of jets can be there. If you have a horizontal shaft turbine, suppose if the shaft is vertical, on one side at the bottom there will be turbine, on the other side of the shaft there may be generator. So such type of turbines are called vertical shaft turbines. Depending on the disposition of the shaft, this will be a horizontal shaft turbine or a vertical shaft turbine. So we have the restriction based on the practical conditions, number of jets. However, depending on the power requirement also, how many jets are needed, how many jets are required to be provided, subject to that maximum number. If a Pelton wheel is provided with more than one jet, it is called a multiple jet Pelton wheel. Otherwise, it is called single jet Pelton wheel or simply Pelton wheel. Single jet Pelton wheel or simply Pelton wheel. But if you have more than one jet, it is called multiple jet Pelton wheel. If P is the power developed by the Pelton wheel working under one jet, the power developed by the same wheel when working under n jets will be n into P. You see here how the power development is. You have only one jet. The power developed is P. You have n number of jets. The power developed will be n into P. So if you want more power, more number of jets are to be provided. More than 6 jets are not provided for a vertical shaft turbine. more than 2 jets are not provided for a horizontal shaft turbine. How many such buckets are provided? Number of buckets. The number of buckets should be as small as possible so as to keep the frictional losses to a minimum. We should not have much of the loss. The jet will always be intercepted by the buckets if the angle between two successive buckets is equal to or less than 20, such that cos theta may be given to be capital R plus small d by 2 by R naught, where R and R naught are referring to the radii with respect to the center of the central axis. So R is the radius of the pitch circle, that means capital D by 2. R naught is the radius of the outer circle. Then the number of buckets jet usually from a thumb rule can be obtained to be capital D by 2D plus 15. This is a thumb rule. D is known, small d is known, capital D is known. So capital D by 2D plus 15 gives you the number of jets, empirical relation for the number of buckets to be provided. Capital D by small d is the jet ratio. So 0.5 plus 1 by 2 is 0.5 plus 0.5 into m plus 15 is the number of buckets which would be provided. So these are all the working proportions. We have seen something like a theoretical velocity root 2gh, actual velocity cv root 2gh, and the actual coefficient of velocity cv to be about 0.9798 or 99, something like that. And the theoretical power is given to be gamma qh, and actual power to be developed is eta naught into gamma into qh, where eta naught is the overall efficiency of the turbine, which is the product of three efficiencies: volumetric efficiency, hydraulic efficiency, and mechanical efficiency. So eta naught is equal to eta hydraulics multiplied by eta mechanical multiplied by eta volumetric. So that is about the actual power developed. Then the jet deflection would be, in the case of Pelton wheel, about 160 to 170 degrees in order to keep the angle phi between 10 to 20 degrees. Average value of 15 degrees may be preferable to achieve the highest hydraulic efficiency. The number of jets of small d can always be calculated based on the total discharge being supplied. Okay, number of total discharge being supplied. So diameter of each jet would be like d. So pi by 4 d square is the area. Pi by 4 d square multiplied by the actual velocity VA gives you the discharge Q. So based on that, you will be able to calculate the diameter small d. Then pitch circle diameter is a capital D, which can be computed like Ku root 2gh would be the velocity, the tangential velocity small u, from which you will be able to calculate the diameter of the pitch circle or mean diameter of the runner. Jet ratio will be capital D by small d, and the value of the jet ratio may be of the order of 11 to 14 for achieving the highest efficiency. For the maximum efficiency, maybe about 11 to 14. The value of m may be about 11 to 14. Then the number of buckets which are required to be provided would be 0.5 m plus 15 or d by 2d plus 15 based on this empirical relation. Okay. So the number of buckets for a Pelton wheel is decided from the consideration that the number of buckets should be as less as possible to reduce the friction loss, and the jet must be fully utilized and no portion of it should have left the runner without doing the work. If it is directly going, what will happen? More and more volumetric losses will be there. If more volumetric losses are there, efficiency of the turbine will come down. So these two assumptions, though contradictory in nature, cannot be satisfied simultaneously. Then we see about the work done by a Pelton wheel. The transfer of work from the jet of water to the buckets takes place according to the simple momentum equation. We use the same notations what we have used in our earlier modules, like impact of jets, hydrodynamic force, hydrodynamic thrust, and application of the momentum equation. Similarly, we are using the same here also. V is absolute velocity of the liquid jet before striking. V1 is the absolute velocity of the jet which is leaving at the outlet tip of the bucket, and u, small u, the velocity of the bucket or tangential velocity of the bucket. Then Vr, the relative velocity, and Vr1, relative velocity at outlet, Vw, relative velocity at inlet, Vw1, relative velocity at outlet, and angle through which the jet is deflected may be 180 minus phi. Phi is the angle at the angle of the bucket at the outlet tip. So the velocity diagrams, if you construct for the inlet and outlet velocity diagrams for a Pelton wheel, may be looking like this. Pelton wheel is a tangential flow turbine. Since the Pelton wheel is a tangential flow turbine, both velocities, that means the velocity of the jet as well as the velocity of the vane, both are in the same direction. If both both V and U are in the same direction, those velocities are called collinear vectors, collinear velocities. Since they are in the same direction, because Pelton wheel is a tangential flow turbine, the liquid jet strikes along the tangent to the path of rotation of the turbine runner. So V and U are in the same direction. So V and U are collinear. That means you have a single straight line. Because V and U are in the same direction, you don't have a separate triangle with the values of alpha and theta. Have you followed this? So V and U will be in the same direction, and hence VR, the relative velocity, will be simply V minus U. The relative velocity will be simply V minus U. After striking here, the liquid jet leaves at the outlet tip with a relative velocity VR1. With a relative velocity VR1. Okay. So the inlet velocity diagram would be something like this, where you have V, the absolute velocity, small u is the velocity of the vane or tangential velocity of the bucket, and hence the relative velocity VR would be equal to V minus U. Alpha is 0, theta is 0. Why alpha theta have become 0 for Pelton wheel? Pelton wheel is a tangential flow turbine. The definition of the tangential flow turbine is the liquid jet strikes the buckets along the tangent to the path of rotation of the bucket. So if you take the tangent to the path of rotation at the point where it is striking, the velocity of the jet and the path of rotation tangent are in the same direction, and hence V and U are collinear. Angle between V and U alpha being equal to 0. Similarly, angle between VR and U theta is also would be equal to 0. Okay, so you have VR, the relative velocity will be simply V minus U. Simply V minus U. What about VW? VW is the Birl component of velocity along the direction of motion of the vane. So V cos alpha in our original case. V cos alpha. Okay. So you have now alpha, angle between V and U, theta, angle between VR and U, and phi is the angle between VR1 and U, beta, angle between V1 and U. Same notations we have been using. The relative velocity VR would be equal to V minus U, and VW would be equal to V, the theoretical velocity, root 2gh, and VF would be equal to 0. V cos alpha, V sin alpha. Okay, so accordingly they are V and 0. Look at the outlet velocity diagram. After striking at the outlet tip, the liquid jet leaves with an angle of VR1. It leaves with an angle of VR1. So this is represented both in magnitude and direction by VR1 here. Then the vane may be moving. The bucket is rotating. Please note that the liquid jet is striking. Where is the liquid jet striking? The liquid jet is striking at the splitter portion of the bucket. At the splitter portion of the bucket. So if you take all the splitter portions with respect to the central axis of rotation, either inlet or outlet are at the same radial distance. That is why you don't have like U1 in this case. U1 also would be equal to U only. So U for the outlet or inlet, and if VR1 is represented both in magnitude and direction, U also is represented in both magnitude and direction. The line joining these 2 points gives you the absolute velocity of the liquid jet at the outlet tip V1, which may have two components, VW1 along the direction of motion of the vane, VF1 normal to the direction of motion of the vane, flow component of the velocity, Birl component of the velocity. This is how the outlet velocity diagram can be constructed. Two important points you need to understand about these velocity diagrams for the Pelton wheel is, point number 1. The inlet velocity diagram for a Pelton wheel is a simple straight line. It is not a triangle. The reason is both the velocity of the bucket as well as the velocity of the liquid jet are collinear velocities. Why? Because V and U are in the same direction, because the liquid jet strikes tangentially to the buckets. So it is tangent to the path of rotation of the bucket, and hence both V and U are collinear velocities, and you have the angle between V and U alpha being equal to 0. This is about one point which is required to be understood. The second point for this is when the liquid jet is striking at the splitter. Where is splitter? The splitter is like two cups joined together, the central portion is the splitter. If the liquid jet is striking at this portion, it is gliding over and leaving at this point. It is gliding, leaving at this point. Striking here, leaving here. With respect to the central axis of rotation, both the points are at equal radial distance. So you have 2 pi r n by 60, 2 pi r1 n by 60, both will become same. R is equal to R1, D is equal to D1 for the Pelton wheel. And hence U is equal to U1. These are the 2 points which are required to be understood. Okay, so outlet velocity diagram. As the water passes over the curved surface of the bucket, VR1 becomes less than VR. This is one point, because you have the frictional losses, you have the impact losses, as a result of which the relative velocity at the outlet would be less than the relative velocity at inlet. So VR1 becomes less than VR due to the frictional losses, and therefore VR1 may be expressed to be equal to K into VR, where K is a factor to account for the losses. If you neglect the losses, the value of K would be equal to 1. Also, as the inlet and outlet tips are at the same radial distance with respect to the central axis of rotation, U becomes U1. U is equal to U1. Then VR1 is equal to K into VR. What is VR? From the inlet velocity diagram, if you see, VR would be V minus U. And VW1 would be equal to, from the outlet velocity diagram, VW1 will be VR1 cos phi minus U1. This is the outlet velocity diagram. So if you take cos phi, you have VW1 plus U divided by VR1. Cos phi is equal to VW1 plus U divided by VR1. Or VR1 cos phi will be equal to VW1 plus U. Or VW1 will be VR1 cos phi minus U. Here U1 theoretically, but since U1 is equal to U, you have VW1 being equal to VR1 cos phi minus U. Okay, so you got now the value of VW1 is known, and VW is also already known to us. What is VW? VW will be V cos alpha. Alpha is equal to 0, and hence VW is equal to V. So at the outlet tip, the three velocity triangles are possible depending on the magnitude of U, corresponding to which you have the value of beta, obtuse, acute, and right angles. But at this stage, for the medium, slow, medium, or fast runners, you may have different, as the inlet and outlet tips are at the same radial distance. U will be equal to U1, and VR1 will be equal to K into VR or K into V minus U. Of course, the value of K always would be less than 1. Okay, so VW1, VR1 cos phi minus U, and VW and VR1 is now replaced by VR here. Why? Because VR1 will be equal to K into VR. So K VR into cos phi minus U. What is VR? The relative velocity, V minus U. Substitute that. K into V minus U into cos phi minus U. Okay, so you have got now VW1. Compute what is the work done. Compute the work done. Work done per second will be equal to W by G, VWU plus or minus VW1 U1. So for the value of beta being obtuse, VW1 will be in the opposite direction, and hence you have VWU plus VW1 U1. So W by G into VWU. What is VW? Middle component of velocity, V cos alpha would be equal to V. Into U plus VW1. Just now we have seen VW1 is equal to K into V minus U cos phi minus U. So K into V minus U, VR is V minus U cos phi minus U into U. So substituting for VR here, it becomes V minus U into cos phi minus U into U. So work done per second will be W by G, V minus U, if you take out common, 1 plus K cos phi into U. So this is the work done per second. If you want the work done per second per unit weight of water, take this W also to the left hand side, per unit weight of water. So work done per second per unit weight of water would be U by G, this small u is brought here, U by G, V minus U into 1 plus K cos phi. Since work done per second per unit weight is calculated, you can compute the efficiency also. So the hydraulic efficiency of the Pelton wheel will be work done per second per unit weight divided by kinetic energy is applied per second per unit weight. So 1 by G, V minus U, 1 plus K cos phi into U divided by the kinetic energy supplied will be V square by 2G. So you have, after simplification, 1 by G here, 1 by G here gets cancelled, 2U by V square into V minus U into 1 plus K cos phi. This is the expression for hydraulic efficiency. At this hydraulic efficiency, eta H could be maximum when it is differentiated with respect to U and equated to 0. So d by du of eta H must be equal to 0, or d by du of what is eta H? Substitute the expression for eta H, 2U by V square, V minus U, 1 plus K cos phi. And you may note that 2 into 1 plus K cos phi by V square is constant, can be taken out of the differential. Take out the differential, 2 into 1 plus K cos phi by V square into differential of U minus U square. So you have V minus 2U is equal to 0. So you have V minus 2U being equal to 0, or V is equal to 2U, or the velocity of the bucket would be equal to half of the velocity of the jet. This is what has been now shown in your video at the beginning, saying that the bucket velocity would be half of the absolute velocity of the liquid jet to achieve the theoretical maximum efficiency. So the condition for maximum efficiency is the velocity of the bucket must be half of the velocity of the liquid jet. Eta H is maximum when the bucket speed is half of the velocity of the jet. So the corresponding maximum hydraulic efficiency would be half of, substituting this value, substituting U is equal to 0.5 V in this. If you substitute here, what will happen? 0.5 V, if you substitute, what do you get here? V is equal to 2U minus U. U divided would be equal to, in this expression you need to substitute. So you have 2U minus U. So you have U, and this is U square divided by 2U whole square. U square gets cancelled, and 2 by 4, or 1 by 2 into 1 plus K cos phi. 1 by 2 into 1 plus K cos phi would be the maximum hydraulic efficiency. Suppose if K equal to 1, when is it possible? When you don't have any frictional losses when the liquid jet is striking and gliding over the surface. Also, when phi equal to 0, the phi would be equal to 0 when you, instead of having a curved vane, you have a semicircular vane. You have a semicircular vane, the value of phi would be equal to 0, with the angle of deflection being equal to 180 degrees. You will be able to get the hydraulic efficiency eta H being equal to 100%. You see, maximum hydraulic efficiency can be achieved, 100% hydraulic efficiency can be achieved, provided that there are no impact losses, there are no frictional losses, and the angle of deflection of jet is exactly 180 degrees. That means whatever the angle, whatever is the direction in which the liquid jet is striking, you should turn back and move in the same opposite direction. That is, the buckets are shaped such that the jet gets deflected through 180 degrees. This is, however, a theoretical value of the hydraulic efficiency. Why it is only theoretical value? When you are keeping exactly semicircular vane, the liquid jet which is entering and leaving in the opposite direction will create a back thrust for the oncoming jets. For the remaining bucket, it gives a back thrust. This will result in a reduced hydraulic efficiency. So the active value of the hydraulic efficiency may be about 90 to 95% because K is not equal to 1 actually, and you can't reduce also further. In actual practice, the angle of deflection cannot be made 180 degrees because in that case, the jet leaving the bucket will strike the back of the bucket, just flowing it, and thus ejecting a retarding force on the bucket. Hence, 10 to 20 degrees is considered to be more and more appropriate. Okay, so keeping the work done principle and the working proportions, how to design this hydraulic turbine, design of a hydraulic turbine. The procedure is a simple step-by-step procedure because we have already seen the expressions for the work done, and we have drawn the inlet and outlet velocity diagrams. Also, we have taken up various working proportions for the Pelton wheel. So what is this hydraulic design for this Pelton wheel? Hydraulic design, I'm telling you, be careful, hydraulic design. So what is required? The procedure is that there would be certain known quantities, there will be certain assumed quantities, and we try to arrive at some other parameters for the turbine runner. So what is it? Known. The power P, the speed N, and head H must be known. How do you know this? Power P, how much power is required to be developed? must be known. How many kilowatts, how many megawatts of power is required? Maybe depending on the say generator concentration, depending on the demand, also depending on the availability of water and head, you will be able to arrive at the power P. The power P. Then the speed of the turbine runner. This will be known from the generator consideration, because generator and turbine runner are coupled to the same shaft. Either horizontal or vertical. On one side turbine runner, on the other side generator. If the generators are required to run at constant speed, the generator speed is known well before 12. So generator speed must be equal to the speed of the shaft, also must be equal to the speed of the runner. So this is how we know the speed in RPM. Then head H will be known because we know where this hydraulic turbine is going to be installed. We know what is the address level, we know what is the tail race level, and the difference between these two is the gross head minus all the losses gives you the net head. Then assume certain values. Overall efficiency may be assumed suitably. Then quotient of velocity, CV value, speed ratio Ku, jet ratio M may be assumed suitably. We have given certain ranges also. If nothing is known, an average value may be assumed initially. The step-by-step procedure, let us see. Determine the required discharge Q. How do you get the discharge Q? The discharge Q based on the equation P is equal to eta naught into gamma QH. Actual power developed would be eta naught into gamma QH, or eta naught is equal to P by gamma QH. You know the power value, so many kilowatts or megawatts. Gamma unit weight of water. Q is the discharge required to be computed. H is the head known. Eta naught overall efficiency assumed. So only unknown in this is the discharge Q. So compute the value of the discharge. Step 2, calculate the velocity V. Calculate the velocity V. So the theoretical velocity is root 2 GH. Actual velocity is CV into root 2 GH. Then calculate the total area of the jets required. The cross-sectional area A would be equal to Q by V. Q is equal to A into V. So from there, compute A. This A will be the cross-sectional area of all the jets. You may have one jet, single jet Pelton wheel. You may have more than one jet also. But this A gives you the total cross-sectional area of all the jets together. So calculate the pitch circle diameter small d. How do you calculate the pitch circle diameter small d? Also called the mean diameter. U is equal to pi d n by 60. From there, you can compute the value of d. Compute the value of d. How do you get U? U would be equal to Ku root 2 GH. Ku is the speed ratio assumed. So Ku root 2 GH gives you the value of the tangential velocity U, and hence the diameter, mean diameter of the runner capital D can be computed. Calculate the required diameter small d of the jet using M is equal to capital D by small d. Jet ratio M 11 to 14, just now we have seen. Maybe assume an average value of 12 if it is not given. So M is equal to capital D by small d. Capital D is already known in the previous step. So substitute that and compute the value of the small d, the diameter of each jet. Now go back to step 3. You have the total cross-sectional area of the jets and you have the diameter of the jet. Diameter of the jet. Total cross-sectional area A. Total cross-sectional area A. Then small d is known. It is the diameter of each jet. If diameter of each jet is known, area of each jet can be computed, pi by 4 d square. So the total area divided by area of each jet gives you how many number of jets are required to be provided. How many number of jets are required to be provided can be known from step 6. Can be known from step 6. Number of jets. Naturally, you will get a fractional value. You will get a fractional value. Something like total area, pi by 4 d square cross-section area divided by area of each jet, pi by 4 d square. So you will get the number of jets small n may be a fractional value. You need to adjust this fractional value to the next higher integer. The fractional number of jets may be rounded to appropriate integral number and calculate the corresponding jet diameter. You need to readjust the jet diameter. Jet diameter already you got from step 5. But here you are getting the number of jets a fractional value. Keeping the area constant, total area required constant, you take n pi by 4 d square is equal to a. Small n pi by 4 d square is equal to small a. Small a is known, and n value has come something like 1.96. You can't provide 1.96 jets. Actually, you are providing 2 jets. N is equal to 2. Substituting the value of n is equal to 2, once again, n into pi by 4 d square is equal to a should give you the value of adjusted diameter. Adjusted diameter. Once you get that adjusted diameter small d, you can calculate the number of buckets, 2 by d by 2d plus 15. Also, you will be able to calculate the dimensions of the bucket, like what should be the radial length and the width of the bucket. The depth of the bucket can be calculated based on the thumb rule which is given. Okay, so hydraulic design in a nutshell includes what and what is required. To start our design of the turbine, we require few parameters, like what is the head available at the hydroelectric power station proposed, what is the speed of the generator which you are supplying, how much power is required to be developed. If these three are known, assume some values suitably, like overall efficiency, speed ratio, then jet ratio, and the coefficient of velocity CV. If these known values are assumed suitably, you have to go step-by-step procedure for finding what? We are finding the diameter of the pitch circle, mean diameter of the runner, diameter of the each jet. How many jets are required to be provided? How many buckets are required to be provided? What is the size of each bucket? This is what is called the design of the turbine. So the outcome from this would be like the diameter of the runner, diameter of the jet, number of jets, number of buckets, size of each bucket would be calculated. Okay. So there is one problem. Just I will explain the problem. You'll be able to do this. The following are the design particulars of a Pelton wheel. Head is given 800 meters. Capital H is 800 meters. The power is given 13,240 kilowatts, 248 kilowatts. P is given. Speed n is equal to 600 rpm. Coefficient of velocity CV is given, and m value is given here. Jet diameter small d would be equal to 1 by 16 capital D. So what is the value of capital D by small d? 16. Jet ratio is 16. Speed ratio 0.46. Overall efficiency 85%. You need to design the turbine. Calculate the total discharge, jet diameter, diameter of the pitch, number of jets, number of buckets, and the dimensions of each bucket. This is what is called the design of a turbine. So eta naught is equal to P by gamma QH. Just follow step-by-step procedure what we have discussed there in the hydraulic design of the turbines. P is equal to eta naught into gamma into QH. Substitute all the values here except the discharge Q. So compute the value of the discharge Q, 1.985 meter cube per second. Then to determine the diameter of the runner capital D, small u is equal to KU root 2 GH, u is equal to pi d n by 60 is equal to 0.46 root 2 GH. Only capital D is not known. Substitute that. So mean diameter of the runner is 1.834 meters. So jet ratio m is equal to capital D by small d is equal to 16. From there you get small d, diameter of the jet 0.114. Number of jets will be equal to pi by 4 d square into CV root 2 GH is the discharge through each jet, and hence the number of jets would be equal to capital Q by small q. You have 2 jets. Once you got the value of the jet, number of jets 2, appropriately adjust the diameter of the each jet. In the earlier case, you have got 0.114 meter is now adjusted to 0.10 meter. Number of buckets d by 2d plus 15, 24 buckets. Number of buckets d by 2d plus 15, 24 buckets. So you have computed the width, the size of each bucket also has been computed. Okay, so this finishes the Pelton wheel, and you have one more problem also in your PDF. You can work for that also. Okay, so thank you very much, and we have finished the Pelton wheel, understanding of Pelton wheel, working of Pelton wheel, various components and function of each component in a Pelton wheel, then working proportions of the Pelton wheel and hydraulic design of the Pelton wheel, followed by we have worked out one problem.